In this example, I'm given the voltages at the terminals of a 4 ohm resistor, and I'm asked to calculate the current through the resistor in two different directions, I1 and I2. Now, since I1 and I2 are assumed to be in different directions, that means that their sign conventions are opposite, and when I finally get done with this problem, the two numbers should be the opposite of one another. First, let's find I1. I1 is assumed positive in this direction. That means that according to the passive sign convention, my positive voltage polarity has to be at that upper terminal. So I'll define this V1 such that assumed positive current enters the assumed positive voltage terminal. Following the passive sign convention is absolutely necessary when you're applying Ohm's law. Now, according to Ohm's law, the current is the voltage difference, which is V1 over the resistance, which is 4 ohms. V1 is equal to the voltage at the positive terminal, which is 12 volts, minus the voltage at the negative terminal, which is negative 4 volts. Always subtract the voltage at the positive terminal from the voltage at the assumed negative terminal to get the voltage difference. This is 16 volts, so from these two expressions, I1 is equal to 16 volts over 4 ohms, which is 4 amps. Now let's calculate the current I2, which is assumed positive in this direction. If I'm going to use Ohm's law, I have to define my voltages and my currents according to the passive sign convention. That means that the positive terminal now has to be at this lower terminal here, and the negative terminal is up here. I'll call this voltage difference V2, and V2 is equal to the voltage at the positive terminal, which is negative 4 volts, minus the voltage at the negative terminal, which is positive 12 volts. That's a negative 16 volts. Now when we apply Ohm's law, I2 is equal to V2 over 4 ohms, the resistance, so it's negative 16 volts over 4 ohms, which is negative 4 amps. So as we expect, the effect of changing the direction on the arrows changes the sign on the value. In this example, we want to find the currents Ix and Iy. Again, these are defined positive and opposite directions, so they should differ by a negative sign. One should be the opposite of the other. We aren't given values for voltages and resistances. So in this particular case, Ix and Iy will be a function of VA, VB, and R1. First, let's take a look at Ix. If I'm going to find this current from Ohm's law, I have to define a voltage such that the passive sign convention is satisfied. That means that assumed positive current enters the assumed positive voltage terminal. So I need to define the voltage Vx this way if I'm going to use Ix is equal to Vx over R1. Current is the voltage divided by the resistance. Vx is the voltage at the positive terminal, which is VA, minus the voltage at the negative terminal, which is VB. So substituting that into the expression for Ix, I get Ix is equal to VA minus VB over R1. Now let's take a look at Iy. Iy is defined such that its assumed positive direction enters this lower terminal. That means that if I assign my voltage unknown, Vy, according to the passive sign convention, the positive terminal has to be down here and the negative terminal has to be up here. Now if I use Ohm's law, Iy is equal to Vy over R1. Vy is the voltage at the positive terminal, which is VB, minus the voltage at the negative terminal, which is VA, over the resistance, which is R1. That's a valid expression, but to make a point, I'm going to change this around a little bit. If I take this negative sign out of this expression and change the order on the unknowns, this is the negative of VA minus VB over R1. So IY is once again the opposite of IX, which is as we'd expect because we've changed our sign convention on those two unknowns.